All right, chapter 5. Now you guys got a test coming up. This chapter is all about rational exponents and radical functions. It also has something called the inverse of a function at the end, which we'll cover. So 5.1 is about radicals and exponents, basically square roots, cube roots, fourth roots, to the power of 2, 3, 4, 5, to the power of n, or to the nth root, right? So there's a variety of rules associated with these exponents and these radicals, and that's what 5.1 goes over. Now, a lot of these you guys have already seen, you've already learned, so this is probably a review, I imagine. The first rule you want to keep in mind is that x to the power of m divided by n, where m and n are both exponents and they're in a ratio in the exponent position. You can translate that to the nth root of x to the m, right? So you can take that fractional exponent and you can turn it into a radical where the root is given by the denominator of the exponent and the inside of the radical is given by the numerator of the exponent. The other one that's important is that when you're raising to a negative exponent, that's really 1 over x to the positive exponent. Okay, so it doesn't make it a negative number, it just causes you to take the reciprocal of it. A couple examples here. 4 to the 1/2 is really the square root of 4, which you can write as just the square root without a symbol, because when it's square root we know that it's a 2 out there, and that's just 2. 3 to the 3/4 would be the fourth root of 3 cubed, which is the fourth root of 27, which is not simplifiable without a calculator. It'll give you some decimal answer. Negative 27 to the 1/3 would be the third root of negative 27. Keep in mind, when you're taking an odd root, you can do it with negatives and still get a real answer, right? So that would be negative 3. Negative 3 times negative 3 times negative 3 is negative 27. Negative 16 to the 1/2, that's the square root of negative 16. That's 4i, for imaginary, right? You can't get a real answer if you're taking the square root or an even root of a negative number, right? And so we put this little I here to denote that it was an imaginary answer. And lastly, 8 to the negative 1/3 is really 1 over 8 to the positive 1/3, which is 1 over the cubed root of 8, which is 1/2. Okay, cool. So let's do a couple of the homework problems here. So first one is 8 to the negative 2/3. So first thing you want to do in this scenario is change it to a positive exponent by rewriting it as the reciprocal, 8 to the positive 2/3. Now I'm going to turn that fractional exponent into a radical equation or expression, where I'll make that the cubed root of 8 squared, which I'll then simplify a little bit. That becomes 1 over the cubed root of 64, because 8 times 8 is 64. And then, is there a cubed root of 64? Yes, there is. That would be 4. So this simplifies to 1 over 4. Okay. Awesome. Looking at number 33, we've got some sphere with an unknown radius, which is what we're looking for. And the volume of the sphere is 216 feet cubed. We know that the volume of a sphere is given by 4/3 pi r cubed. That's just a formula you have to know, unless they give it to you, of course. And all we do to solve for the radius is just set the volume that we're given, 216, equal to 4/3 pi r cubed. And we'll just start solving for r, right? So we'll multiply both sides by 3 over 4 to get rid of that 4/3 in the front. 216 times 3 over 4, that's 54 times 3, which is 162, equals pi r cubed. And then we'll divide both sides by pi, which gives us r cubed equals 162 over pi. And then to get r by itself, you take the cubed root of both sides, which will undo the cube on the r and put a cubed root over on the right side. Now, is there a cubed root of 162? Let me think. Probably not. No, there's not an even cubed root of 162, so you would need a calculator for this part, which I'm not going to do. You can throw this into a calculator, and you'll get some decimal answer. We can probably approximate it. Let's see. 162 divided by pi, we'll just say that's 162 divided by 3 for simplicity, so that's 54 approximately, and then the cube root of 54 is going to be somewhere between 3 and 4. So it's going to be closer to 4. So it's probably around 3.8. Okay? And you can do that with a calculator to figure that out really easily. All right, in this last one, x to the 6 plus 36 equals 100. So quite straightforward to solve something like this. You'll just start subtracting 36 from both sides, which will give you x to the 6th equals 64. And then you'll just take the 6th root of both sides, which will get rid of that exponent of 6 on the x. Now the 6th root of 64, you probably know, is 2. And so you get x equals 2. Boom, nothing crazy about that. All right, so don't forget your exponent and your radical rules. That's how those work. 5.2, properties of rational exponents and radicals. This is very similar to 5.1. We're just going over other properties. In this case, when you have multiple terms and you're multiplying them, dividing them, raising an exponent to an exponent, things like that. So check out these rules in this red box. If you're multiplying two numbers with the same base, you add the exponents. If you have a number raised to an exponent in parentheses with another exponent outside, you multiply the exponents in that case. If you have two numbers in parentheses raised to an exponent, you apply that exponent to both numbers. We talked about this one earlier. Anything to the power of 0 is 1. When you're doing two numbers divided by each other, the same number, you subtract the exponents. Keep in mind, this number that you're dividing has to be the same number. You can't do it with a 3 here and a 2 here. They both have to be a 4 and a 4, or a 5 and a 5, etc. And then you've got some radical properties. If you've got two of the same radical, so cube, square root, cubed root, fourth root, etc., and you're multiplying those, you can just multiply the numbers together and then put them under one radical, right? The same holds true if you're dividing those numbers. Each thing can go under their own radical. All right, looking at a couple of examples here, x cubed times x to the 4th, you just add those, so that's x to the 7th. X squared to the power of 5 multiplies those, so you get x to the 10th. Square root of 2 times square root of 18, that becomes square root of 36, because 18 times 2 is 36. Square root of 36 is 6. And then last example, cubed root of 8 over 27, that can become the cubed root of 8 divided by the cubed root of 27, which is 2 over 3. And then we've got some homework problems. Okay, so one thing I didn't talk about is something like 29. If you have 1 over 1 plus square root of 3, in order to simplify this, you have to multiply the numerator and the denominator by what's called the conjugate of the denominator. And to find the conjugate, all you do is you switch the plus sign between the two numbers into a minus sign. Or if you started with a minus sign, you switch it into a plus sign, right? So you'd multiply this by 1 minus the square root of 3 over 1 minus the square root of 3, which we'll just do some math now. So 1 times 1 minus the square root of 3 is 1 minus the square root of 3 over. Now I'm going to FOIL out the bottom. 1 times 1 is 1. 1 times minus root 3 is minus root 3. Root 3 times 1 is positive root 3. And then root 3 times negative root 3 is negative 3, right? When you multiply a square root times the same square root, it's just the number inside. It cancels out the square roots. Now if you simplify this, you can see the two radicals in the middle cancel out. And so you get 1 minus 3 on the bottom, which is just negative 2. And so there you have it. Now you don't have that radical in the denominator, which is technically improper, right? So you can do what's called rationalizing it by using a conjugate in this case to fix that problem. All right, number 25, the square root of 3 over 8. That can be turned into the square root of 3 over the square root of 8. Now, once again, we have a radical in the denominator, which you want to simplify by rationalizing. In this case, all you have to do is multiply by the square root of 8 over the square root of 8, which gives you the square root of 24 in the numerator over 8 in the denominator. Now you can simplify the square root of 24. So the square root of 24 is equal to the square root of 4 times the square root of 6, which is equal to 2 root 6. Okay, so this becomes 2 root 6 over 8, and you can cancel out a 2 from the top and the bottom, which becomes root 6 over 4. Great. All right, number 54, we've got something slightly more complex, but really not that hard. The 8th root of n to the 18th times p to the 7th, all divided by n squared times p to the negative 1. So we're going to apply a couple of different rules here. Start by rewriting our radical. Now, n to the 18th divided by n squared is just n to the 16th. And that p to the negative 1 in the bottom, well, we'll just do it this way. P to the 7th divided by p to the negative 1. P to the 7th divided by p to the negative 1. That's just p to the 7 minus negative 1. Okay, 7 minus negative 1 is 8. So that becomes p to the 8. Alrighty, sounds good. Now you just simplify this. You can turn it into the 8th root of n to the 16 times the 8th root of p to the 8. 8th root of n to the 16 is just n squared. You just do 16 divided by 8. And then 8th root of p to the 8 is just p. There you have it. N squared p is the simplified answer. Alright, 5.3, graphing radical functions. A couple of important things to note here. Square root of x is our parent function, and that has this shape. Okay. Notice that it does not extend into negative x values. Okay, the domain is restricted to only positive values for x. Okay, the range as well. The range is restricted to only positive values for y. It's only in quadrant 1. And you can kind of think about why that is, right? What's the square root of negative 4? It's not real. It's too imaginary, which doesn't show up on a real coordinate plane, right? Now the cube root of x, the parent function for cubics, is for cubed roots, is different, right? That has a domain of all real numbers. That has a range of all real numbers. There's no domain restrictions on that function at all. Okay, cool. So I figured we could just jump right into the homework problems for this one because that's probably the best way to go about learning it. So for these, it wants us to match the function in 3 through 8 with the given graph. All right, so let's do that. So first one on number 3, square root of x plus 3. When you add this 3 inside the radical, what that does is it takes our parent function and it just shifts it 3 units to the left. Okay, when you're adding the 3, that shifts it 3 units to the left. Great, so which one took our parent function and shifted it 3 units to the left? Well, this one, instead of starting at 0, starts at negative 3, which means it shifted it 3 units to the left. Okay, so number 3 is B. Great. Number 4, square root of x plus 3, where the 3 is outside of the radical. Okay, when you have a plus 3 outside of the radical, that shifts the function up by 3 units. Takes the parent function and shifts it up by 3 units. Which one has done that? Well, if you look at D, instead of starting at 0, 0, it starts at 0, 3. Shifted it up by 3 units. So D is the answer for number 4. Number 5, square root of x minus 3. Okay, this is very similar to number 3, except instead of a plus 3, it's a minus 3. If a plus 3 shifted it left 3 units, what do you think a minus 3 does? You're right, it shifts it right 3 units. Okay, F, instead of starting at 0, 0, starts at 3, 0, so it shifted it right 3 units. All right. Number 6, square root of x minus 3. Once again, very similar to number 4, we're shifting the parent function down by 3 units. Okay, which one is shifted down 3 units? Looks like A, right? Great. All right, number 7, we're just combining all those things. So number 7, we've taken the parent function, we've shifted it left 3 units and down 3 units. So left and down would be E. And then via process of elimination, there's only one left, which is C, right? That one's right 3 units and up 3 units, which you can see is exactly what happened. All right, great. Okay, in these exercises, we want to describe the transformation, and then we want to graph the function. All right, so I'm not going to graph every single one of them just because there's a lot, but let's talk about the transformation for each. So on 19, we took the parent function square root x, and we turned it into square root x plus 1 plus 8. Okay, so what did we do? We shifted it left by 1 unit and up by 8 units. Okay, the left by 1 unit is because of the plus 1 inside the square root, and the up by 8 units is because of the plus 8 outside of the square root. All right. I'll do the graphing after we talk about the transformation for each. On number 20, square root of x turns into 2 times square root x minus 1. Okay, on this one we've shifted it right by 1 unit. Now what does the 2 out front do? That's a vertical stretch by a factor of 2. By a factor of 2. Okay, so what does that mean? That means it takes the function, the regular function, and essentially makes it 2 times taller. Okay, that's what a vertical stretch does. We'll graph that one just so you can see. Let's actually start by graphing that one now just so we can do that. Okay, so I'm going to graph both the parent function and the new function. Alright, so the parent function I'll do in purple. So 0, 0, 1, 1, 1, 2, 3, 4, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 3. Alright, here's the parent function, square root of x. Boom. Okay, so on 20, we're taking that function and we're shifting it 1 unit to the right, and then we're multiplying each y value by 2. Okay, so 0, 0, 0 will shift to the right by 1 unit, and then we'll multiply that by 2. That's still 0, 0 because 0 times 2 is 0. The next point, 1, comma 1, we're shifting over to x equals 2, and then we multiply 1 by 2, so that's 2. Okay, the next point is 4, comma 2. That becomes 5, comma 2, and then it becomes 5, comma 4. Okay, multiplying that. The next point, 9, comma 3, becomes 10, comma 6. Boom, and you can see how we shifted it 1 unit to the right, and then we also made it taller, twice as tall. Right, all we did was we took each y value from the original points and we multiplied them by 2. Okay, if you can't figure that out, you can also just easily make a table. Right, you can make a table of x and y values. You can plug in some values for x, and you can see what the values are for y. All right, great. Let's talk about 22. We'll do 22 now. So 22, we are taking the cube root function and we're shifting it left by 4 units. That's the plus 4 inside, and down by 5 units. That's the minus 5 outside. Okay, and we'll graph that one just so you can see that as well. Okay, here's the parent function, cube root x, 0, 0, 1, 1, and then 1, 2, 3, 4, 5, 6, 7, 8. Notice I'm just choosing very even points, right? So when x equals 8, y equals 2, that's why I'm choosing these points. 1, 2. Okay, here's our parent function in purple. Now what did we do? We took this function and we shifted it left 4 units and down 5 units. Okay, so we're going to take each point and we're just going to shift them left by 4 and down by 5. Okay, so 0, 0 becomes 1, 2, 3, 4, 1, 2, 3, 4. Okay, I got to move my graph up because I won't have enough room otherwise. Okay, so I'm going to take 0, 0 and I'm going to go left. Hold on. Zero, 0 is going to go left by 1, 2, 3, 4, and down 1, 2, 3, 4, 5. Great, there's my center point. Then I'm just going to go over 1, down 1 from there to match the other point that I had here. And then I'm going to go over 1, up 1 from there to match the other point that I had here. And then I'm going to take each of my other points and move them. So 8, comma 2 becomes 4, comma negative 3. And then negative 8, negative 2 becomes negative 12, comma -7, which I don't have enough room for. So we will just approximate that point. You get the idea. Great. All right. On these ones, we want to identify the domain and range. That's something that's quite important. Okay, so keep in mind, on square roots or even root functions, we have a domain restriction where you can only have positive values under the radical. Okay, that is not the case for cube roots. Okay, so in this one, square root of x minus 3, the easiest way to figure out the domain is to simply just take the radicand, the thing inside, and just set it greater than or equal to 0, okay, and solve for x. So x is greater than or equal to 3. If you want to write that in interval notation, you can do bracket -3 comma infinity. That's the domain. Okay, great. For the range, you want to figure out what's the smallest y value that you can get. Well, when x equals 3, you get 0 in the radical, which means 0 would be the smallest y value you can get. So 0 comma infinity would be the range because it can go up to infinity. When x is infinity, so is y. Great. This next one, -3 times x plus 1 to the 1/3. Remember, you can rewrite that as -3 times the cubed root of x plus 1. All we're doing is taking our cubed root function, shifting it 1 unit to the left, reflecting it across the x-axis. That's what this negative out front does. And then vertically stretching it by a factor of 3. That's what this 3 does. Okay, but that doesn't do anything to the domain and the range, right? You can transform a cube root function or an odd root function any way you want without changing the root. Meaning, if you're not actually changing it from a cube root to, say, a square root, as long as it's retaining the fact that it's a cube root, the domain and range will never change. They're always going to be the exact same thing of -infinity to infinity and -infinity to infinity. That's for the domain and the range consecutively, okay? Or you can write all real numbers, whatever you prefer. Great. This last one, h of x equals -4th root of x. This one is a little different. Let's go ahead and graph this one just so you can see how it's different. It's not that much different, but it's a little bit different. Like that. Okay, I'm going to make a table here just so that this is a little more obvious. So x and h of x. When x is 0, x is 1. Then we'll choose when x is 16 and when x is 81. Okay, so we're going to plug in 0 for x. 4th root of 0 is just 0. We're going to plug in 1 for x. 4th root of 1 is 1. Make sure you put that negative out front. Plug in 16. 4th root of 16 is 2, so that's -2. Plug in 81. 4th root of 81 is 3, so that's -3. Notice how I strategically chose my points. Now I'm going to have to estimate a little bit here because I obviously don't have enough room to go all the way up to 81. But I will do my best here. So 0, 0 would be here. 1, -1 is here. 16, -2, we'll say is like right here. So we're changing our axes a little. And then 81, -3, we'll say is like here. Great, so notice we reflected across the x-axis. Now we're in this bottom quadrant, okay? So the domain is still the same as the square root function. It's still 0 to infinity, including 0, but the range has now changed, right? So the lowest number the range can be is -infinity, and the highest number it can be is 0. Okay, so this is for the range, this is for the domain. So make sure you're keeping track of whether you have a negative leading coefficient or not, because that will change the domain and the range on a even root function. On an odd root function, it does not matter. You can change it any way you want, and you're always going to have the same domain and range of negative to positive infinity. Great. 5.4, solving radical equations. All right, so I just went straight to the problems on these because these are quite similar to things you've probably done in the past. So for number 3, you just start by square rooting both sides. So you start by squaring both sides, raising both sides to the power of 2. That'll cancel out the radical on the left. turn 6 into a 36. Subtract 1, divide by 5, x equals 7. Great. One thing you do want to do with these is you want to check for extraneous solutions, meaning you want to plug your number back in and see if it makes sense. So plug it back into the radical. So square root of 5 times 7 plus 1. 5 times 7 is 35 plus 1 is 36, which is 6. So that works out. Sometimes it won't work. That's why you have to check for extraneous solutions. On this next one, you can start by subtracting 10. You'll have 1/5 cubed root 3x equals negative 2. You can multiply both sides by 5 to get rid of that 1/5. And then you can cube both sides, raise both sides to the power of 3. And then you can divide by 3. X equals negative 1,000 over 3. And then on this last one, you will start by squaring both sides. So you'll do square root 3x minus 8 plus 1 to the power of 2 equals x plus 5. The squaring the right side just gets rid of the radical. Notice it doesn't on the left because of that plus 1. That on the left, we have to FOIL out this binomial, right? So this would be square root of 3x minus 8 times square root of 3x minus 8, which is just 3x minus 8, and then plus 2 times square root 3x minus 8. That's because I did square root of 3x minus 8 times 1, and then 1 times square root of 3x minus 8, which gives me 2 of those. And then plus 1 equals x plus 5. We can simplify by moving stuff over to the right side. We'll have 2 times square root 3x minus 8 equals negative 2x plus 12. Divide both sides by 2, we get square root 3x minus 8 equals negative x plus 6. Now we can square both sides, which will give me 3x minus 8 equals negative x plus 6 quantity squared, which is x squared minus 12x plus 36. Simplify by getting everything on one side. X squared minus 15x, and then plus 44. Now this is a quadratic that factors to x minus 11 times x minus 4. And then you can just set that equal to 0, solve for x, and you get x equals 11 comma 4. Okay, now you want to go back and check, are those answers okay? Right, so plugging in 4 up here, 3 times 4 is 12, 12 minus 8 is 4, that's fine, you can have a square root of 4. 4 plus 5 is 9, square root of 9 is fine. Plugging in 11, you also get fine answers. Things that wouldn't be fine is if you got a negative under the square root. If one of your x values gave you a negative under a square root, that's not okay. That means it would not be a solution. Okay? Alright. And now we've got these inequalities. Okay, so they start the same way as the equations. There's just one different step at the end. So you'll start by dividing both sides by 4. Square root x minus 2 is greater than 5. Square both sides, x minus 2 is greater than 25. Add 2, x is greater than 27. Great. Now, there is one other thing. You have to remember that there's a domain restriction on these square root functions where x minus 2 has to be greater than 0. So you take the radicand and you set it greater than 0. Sorry, greater than or equal to 0. And so that means x is greater than or equal to 2. So that means x is sorry, let me think about how this one works out. Greater than 20, let's see, greater than 5, square root of 20. X is greater than 27, or x is greater than or equal to 2. Well, x is greater than 27 is included in x is greater than or equal to 2. So let's see, how does that work? Oh, I see. Because x has to be greater than 27, you don't need to include this second part, right? If this had been a less than, that's when this would have been important, but because it's a greater than, we already have to be greater than 27, which isn't going to be a problem with our domain restriction. So it's just x is greater than 27. All right, great. On this other one, you can start by dividing both sides by -2. You get cubed root x plus 4 is greater than -6. Notice how I flipped the sign because I divided by a negative. You can cube both sides. X plus 4 is greater than -216. Subtract 4, x is greater than -220. All right, awesome. And you don't need to worry about setting the radicand greater than or equal to something because this is an odd root function and those do not have a restriction on their domain. Great. All right, section 5.5, performing function operations. This one's quite simple. I'm not really sure why this is included, but it's just talking about how you can add functions or divide them or multiply them, which I think you already knew. So this first question wants you to add f of x and g of x, subtract f of x and g of x, and then plug in 16 and see what you get for both. So we'll start with f plus g of x, f of x plus g of x. That's -5 4th root x plus 19 4th root x. That just becomes 14 4th root x. Okay. Then we'll do f of x minus g of x. That's -5 4th root x minus 19 4th root x. That's -24 4th root x. Great, and then it just wants you to plug in 16 for x on both of those. 4th root of 16 is 2. 14 times 2 is 28. And then 2 times -24 is -48. Great. All right, this next one wants you to multiply the functions and then divide them. So f of x times g of x, which note, you can write that like this as well, right? This right here means the same thing as this right here. Okay, so 2x cubed times cubed root of x is just equal to 2x cubed cubed root of x. That's not simplifiable, right? That's as simple as it gets. F of x divided by g of x is equal to 2x cubed divided by the cubed root of x. Now keep in mind you want to rationalize this because you don't like to have radicals in the denominator, so you can multiply this by the cubed root of x squared over the cubed root of x squared, which becomes 2x cubed cubed root of x squared over the cubed root of x cubed, which is just 2x cubed cubed root of x squared over x, because cubed root of x cubed is just x. Okay, you can simplify that further. It becomes 2x squared cubed root of x squared. Great, and that's it. I'm not going to plug in -27. That's pretty trivial. You can just do that and see what you get. All right, and last section, inverse of a function. This one's quite interesting. So first thing that I want you to know about an inverse of a function is that when you have a function and its inverse, you can write them like that. Okay, so f of x is the regular function, f to the -1 of x is the inverse of the function. Okay, now the domain and the range of the regular function are swapped on the inverse. Okay, so the domain of the regular function becomes the range of the inverse function, and the range of the regular function becomes the domain of the inverse function. Okay, so let's take a look at some more examples. So let's say I had the function f of x equals 2x plus 1, and let's say I wanted to find the inverse of this function algebraically. All you have to do is start by, I like to turn f of x into y for this, so y equals 2x plus 1. You start by swapping the place of x and y, literally just switching the places of them, and then you solve for y. Okay, so subtract 1 from both sides, and then divide by 2. So y equals x minus 1 over 2. Okay, great. Now, something important to note about a function and its inverse is that if you were to graph a function and its inverse, like these two functions that we just worked with. So I'm going to start by graphing 2x plus 1 Okay, so 0 comma 1 is the y-intercept, up 2 over 1, down 2, back 1. So here's 2x plus 1. And then its inverse is y equals 1/2 x minus 1/2, which we solve for here. So we're going to go down 1/2, 0 comma 1/2 is the y-intercept, and then from there we go down 1 over 2, and we go up 1, back 2. So there's that function. Now if you notice, these two functions are exact reflections of each other across the line y equals x. Okay, so 1, 2, 3. So the line y equals x is the plane of reflection, is the line of reflection in which a function and its inverse reflect across. Okay? So anytime you have a function and its inverse, they're always reflections of each other across the line y equals x. Okay, and that's why the domain and the range are flipped, because of that fact right there. Okay, cool. So let's take, let's do a little practice here. So let's say we had the function f of x equals 2 times x plus 1 squared, and we wanted to find f inverse of x, so the inverse of that function. So you start by switching f of x for y. Then you swap x and y. Then you just resolve for y. Okay, so this is 1/2 x equals y plus 1 squared. Square root both sides. Square root 1/2 x equals y plus 1. Now, remember, when you take the square root of both sides and there's a variable on either of the sides, you have to do the positive or the negative answer. Right, so this is really plus or minus square root 1/2 x. So y equals -1 plus or minus square root 1/2 x. Okay, that's the inverse of the function. You can write it as y, or you can write it as f inverse of x. It doesn't matter. Actually, I would write it as f inverse of x, just so there's no confusion. Okay, let's evaluate the domain of the original function. So this is a quadratic, so the domain is always all real numbers. And then the range, the vertex of this function would be the lowest point, the lowest y value, because it has a positive leading coefficient. So the lowest y value would be 0 or -1 comma 0. 0 would be the lowest y value, so the range is from 0 to infinity, including 0. Now, if you were to look at the inverse, you would find that the domain of the inverse would be from 0 to infinity. And you would find that the range was from -infinity to positive infinity. Okay? See if you can figure out why. That would be a good practice to see if you can identify that. Okay, great. Now, if you guys have any questions while you're studying, obviously feel free to reach out. I hope that was helpful.